So the goal of today's video is to go over section 2.6, which is solving absolute value inequalities. The first part of our understanding and how we're going to do this is revisiting absolute value and making sure that we understand that absolute value is a measurement of distance. That is, whenever I see this absolute value symbol, like the absolute value of x is equal to 6, I can replace that word with the English word distance. So distance is 6. Now, what we're going to first do is we're going to investigate that distance and see the distance that I'm looking for, whether it be 6 or more than 6 or less than 6, will help us solve absolute value inequalities. And what we're going to realize is that absolute value inequalities are a special form of compound inequalities, meaning we will need to relate them to some form of the and or the or inequalities. So that's what we're going to go first look at real fast here. So we have these quick little warm-up questions that you're welcome to follow along with. And number one here, what they want us to do is shade all the numbers that are exactly 6 units away from 0 on the number line. So if I start at 0, I can count 6. And this number right here is exactly 6 away. It's the number 6. So I'll measure that. I'll just show I started at 0 and I traveled 6 units. I could also go 6 units the other way though. So if I go the other way 6 units, again, the same distance, it just brings me to a different number. This number right here is exactly 6 away. So we are measuring a distance, right? So in this case, we're finding the absolute value of x that was equal to 6. That's kind of what we just did here. So over here, what we're going to just kind of remind ourselves is if we have anything that looks like this, so it could be x minus anything inside the absolute value is equal to a number. The way that we'd think about this, let me change some colors here. If it's equal to a number. So whenever we see an equal sign, what we're thinking is we replace that absolute value with the word distance. So distance. And then the equal sign means is exactly. And then whatever that number is, doesn't really matter. Like in the example over here, it was 6. Maybe I could change that to 12 or 15 or 22. So when I see an equal, I know that we're looking for an exact distance. When we come down here, they want us to shade all the numbers that are more than 6 away. So if I started at 0 and I went 6 to the right, that would bring me to the number 6. But this number is not more than 6 away. It's exactly 6 away. So it doesn't work, so we'd put an open circle there, but everything to its right is farther than 6 away, right? If it's exactly 6 away is right here at 6. Stuff like here, this is like 9 away, this one is 10 away, so everything I've shaded in is more than 6 away. But of course I could do that in the opposite direction. If I go 6 this way, that would end me at the number -6, but -6 isn't more than 6 away, it's exactly 6. So if I want more distance, I'd have to go further this way. So that brings up a really main idea. When we want more distance than something, like if I want the distance to be more than 6, I have to move away from something if I want to increase the distance. So if I see the word more distance, I need to move away from something. In this case, it was 0. So what we can see then is if we were thinking about distance, just any old absolute value, there could be anything inside there. If we see that distance is more than a number, well, what we can see here, let's first write it as an English sentence. So if our distance, and then that inequality symbol, it says is more than, and that number could be anything, right? In this case, it was 6. What we see is it creates an and graph. An or graph. Those graphs go away from each other. I have all the x's that are less than -6, or I have all the x's that are greater than 6. So when I see that distance is more than something, this creates an or compound inequality. Now when I go to the next example, rather than a distance being more than 6, they want a distance that's less than 6. So we'd kind of go through the same argument. If I start at 0, 1, 2, 3, 4, 5, 6 is exactly 6 away. Now that doesn't satisfy the requirements. So I'm not going to shade it in, so I put an open circle. But if I want less than 6, that means I'd have to go towards 0, because all these numbers like 5, 4, 3, 2, and 1 have a distance that's less than 6. And 0 is exactly 0 away from 0, so that is less than 6. But nobody said I had to go 6 to the right. I could have counted 6 to the left and ended up here. Now that number is -6. That also doesn't work because -6 is exactly 6 away. But I wanted less than 6. So if I want to decrease the distance between -6 and 0, I'd have to go towards 0. So when I see a distance that's less than something, if I want to decrease my distance, I'm going to have to move towards something. In this case, I'm moving towards the number 0. So in general, if we have an absolute value, and inside that absolute value could be anything, if I see that that distance is less than something, and that thing could be any old number, what we want to see, so let's write that in English first. If distance, because absolute value is distance, and then we see this means is less than, and that number just represents any number. So if our distance is less than a number, we can clearly see that this creates an and compound inequality. And that's going to be our first major task when we're dealing with absolute value inequalities. So let's go back to our note page. So we've kind of seen that absolute value will always be related to and versus ors. And the distance that we're looking for, more or less, will relate to the and or the ors. So the way that we're actually going to solve these, we're going to do some examples now. I do have a list of steps written down that you're welcome to pause the video and just copy right now. But what we're going to do is we're first going to try to see if it's an and or an or. Then we're going to write the inequalities and we're going to solve them. And then we'll graph them and look for our final answer. So again, if you want to pause and write down the list of steps, please do so now. Well, let's just look into number 1. So we can see that we have an absolute value symbol. So that's right here. And then I can clearly see an inequality. So here's our inequality symbol. It's compared to some number that's called 2. And like I said before, here is our absolute value symbol. So the first thing we do when we try to solve these, we want to make sure the absolute value is alone. We want to get distance all by itself. In this case, it is. And again, I can just visualize it's on its own side. It's on the left side of the less than sign, and it's by itself. So what we need to do then is figure out whether it's going to be an and or an or. And this is just what we were practicing. Whenever I see absolute value, that's the word distance. And it's being compared to the number 2. And since the inequality symbol is opening towards the 2, that means the 2 is the biggest, which means my distance is less than. In this case, or equal to. But anytime we see a less than distance, we know that less I'd have to get towards. I'd have to move it towards it if I wanted less distance. I'm going to have to use an and compound inequality. So our first step just tells us that this is going to be an and compound inequality. So what we need to do then is we need to write 2 separate inequalities connected with that word. So I just like to put and in between them. Now, when we write those 2 inequalities, it's going to seem very similar to how we wrote 2 equations when we solved absolute value equations. We have our positive version and our negative positive version. So if you need to review that, please go back into 1.4 and find when we solved absolute value equations. So I'm going to come back up here and we're going to write our positive version and our negative positive version. So if I take this, so it'd be x plus 3, and I keep the symbol. That's our positive version. And then for our negative positive version, whatever was inside the absolute value, I group it so I can take the opposite or the negative of it. And I leave everything else the same. So what we're going to do is we're just going to solve and graph each of those inequalities separately. So I'll go work on the blue one. So if I wanted to get x alone, I would simply subtract 3. So I have all the x's that are less than -1. Again, these are connected with the word and. And then I'd solve this one over here. So I distribute. So -x minus 3 is less than or equal to 2. Add 3 to both sides. Now here when I divide by the negative, don't forget to flip the signs. So I need to graph x is less than or equal to -1 and x is greater than or equal to -5. So we'll graph them separately. So over on our number line, we'll place -1 right here. I want all the x's that are -1 or less than that. So that's this way. Now the other inequality, I want all the x's that are -5 or greater. So here's -5. I do want that, and I want everything that's greater. Now our final step in solving this is look for the final solutions based on and or. So what we mean by that is and means both are true. So on my number line, where did I shade things that are both blue and red? Well, I can see that in between these numbers, I've shaded blue and red. Now -5 is blue and red, so I would include it, and -1 is blue and red, so I'd include it. So if I was making like my final answer in black here, I can see that I've created an and inequality. I'm just gonna clean up the stuff that I don't need. And this would be our final answer. So let's try the next one. So first thing we need to do is make sure the absolute value is alone. Here it is, it's all by itself. So then I ask myself if this is an and or an or, so I can see that this distance is less than something. Now if it's less than something, this is less than -2. This is actually a special case. So it's good to talk about. We know absolute value is always 0 or bigger. So there's never going to be an absolute value that's less than a negative, because it can't be negative at all. Another way we could think about it is distance can't be less than a negative. There is no negative distance. That doesn't make any sense. So if there's no negative distance, how can I be less than a negative? So it's kind of a special scenario, very similar to when we have like an absolute value of x is equal to a negative. We knew that meant no solutions. So then on our number line, we simply just wouldn't shade anything in. There's no solutions. Let's look at example number 3. Step number 1 is making sure the absolute value is all by itself, which it is. And then I look at the inequality symbol and notice that it's eating the 11. So if it's eating the 11, that means the 11 is biggest. That means the distance is smaller or less than 11. So if our distance is less, as we started this video with, any distance that's less is going to be an and inequality. So this too will be an and inequality. So I just note myself that this will be an and. Step number 2 is then to write our two absolute value, or excuse me, our two separate inequalities, and we're going to separate them with the word and. So we have our positive version, and that's where we keep everything the same. Let's just solve that right away. So we get that w is less than 6. So we can go graph that right away. Let's just put 6 right here. So all the w's that are less than 6, I don't want 6, but I want the numbers that are less than it. So I'd go this way. That was our positive version, and we know that there's going to be another one connected with the word and. And our other version, just like we did with equations, is our negative positive version. So we'd want to take the negative or the opposite of whatever was inside the absolute value. Keep everything else the same. So we distribute the negative, subtract our 1. Now again, when we divide by a negative, we just got to remember to flip the sign. Now let's go graph that. All the w's that are greater than -5. So here's -5. I don't want -5, so I'm going to leave it open. I'm going to shade all the numbers that are bigger than that. So then our last step, step number 5, is making sure we do our final answer based off of the and or the or. So and means both. So where are they both shaded in? So where is it blue and red? I can see they start to be shaded in at -5 and they stop at 6. So -5 and 6 have all my x's in between. 6 is not included and neither is -5, so I don't do the equal. Just gonna make my final answer very clear. So shade that in nice and black. And then I have the ability to erase all my other stuff. So I can see the final answer, all the x's between -5 and 6, but not -5 and 6. A few more examples to do today. Let's look at number 4. So the first step is making sure that the absolute value is all alone. So I can see that absolute value right there. And here's my inequality symbol. And I'm noticing right away that the inequality symbol is facing the absolute value, which tells me that it's eating the distance. And if it's eating the distance, that means the distance is the biggest. So the distance is more than something. It does say equal to, but more and equal to will handle that, but it's more than 3. So if the distance is more, according to what we investigated before, if I want more distance, I have to move away. So this is an OR graph. So when I come down here, I know that that would tell me that this is an OR graph. So we will continue the process the same. We're going to need to write two inequalities, just separated by the word or. So one of them is our positive positive, and one of them will be our negative positive. So we'll do one at a time. Let's do our positive positive, which is pretty much keep everything the same. So I'll subtract 1 from both sides, so I get all the x's that are greater than 2. And there's going to be this other inequality that's or. So we'll solve the negative positive, which means I want to take the absolute value thing and take its opposite and keep that. So I'll distribute the negative, so negative x minus 1 is greater than or equal to 3. Add 1 to both sides. Now again here, I have to divide by a negative, so I have to flip the sign, so I get all the x's are less than or equal to negative 4. So the next step is graphing each of those inequalities separately. So I want all the x's that are less than negative 4. So on our number line, we'll place a negative 4. And I do want to include negative 4 because of the equal, and we'll shade all the numbers that are less. The other inequality was all the x's that were 2 or greater. So on our number line, we'll estimate where 2 is, just about right there. I do want 2, and then I want all the numbers that are greater. Now with this case, the word or means either or, not both. So they combine their powers. In other words, what's shaded red or blue? Well, we write our final answer because we know this is an or. So we have all the x's that are less than negative 4 or all the x's that are greater than or equal to 2. And this would be our final answer. It's okay if we want to come back over this and shade it nice and black so we know exactly this is our final answer. But OR graphs should always go away from each other. If I want more distance, I need to go away from something. So these graphs are going away from each other. Let's look at our next one. The first thing we want to note is the absolute value all alone? And in this case it is. And I'm noticing that the inequality symbol is eating the absolute value, and it's comparing it to the number negative 5. Let's think about that. If we were saying that the distance is more than negative 5, well, we said up top here that distance could never be negative. So in other words, all distances that we could measure are positive. So no matter what number I plug into the absolute value, whatever this is, it's going to be bigger than or equal to 0. So if it's never going to be a negative, that means its absolute value will always be bigger than a negative. So this is an example of all real numbers. So again, it's one of those special cases, but we know that distance is always more than a negative. So what numbers would make this true? Well, what we'd have to do is we'd actually have to shade in everything, because every single number on the number line has an absolute value that's greater than a negative, because every single number has an absolute value that's at least 0, if not positive. So we can see in example number 6 now as we progress forward, the absolute value symbol is not by itself. So before we can do anything with distances, we need to isolate that. So in other words, we'd undo these operations. So we start by undoing addition and subtraction. So I have 3 times 2t minus 3 inside the absolute value is greater than 21. And recall, if there's no symbol between two things, no plus or minus or divide or multiply, that means it is multiply. So to undo multiplying the absolute value by 3, we would divide by 3. Now the absolute value is isolated, so I can pick back up at where I started. Now you might want to go back to your list of steps and add, make sure it's isolated on its own. If not, you need to get it isolated. That's our first step then. So down here, once it is isolated, we just pick up from where we left off. I can clearly see that that distance is greater than the number 7. So if distance is greater, or in other words, distance is more always leads to or. Because if I want more distance, I have to go away from something. So those graphs would be going away from each other. And then we already know how to solve this, so we'd start our positive version. So 2t minus 3 is greater than 7. So adding 3 to both sides and dividing by 2, we get all the t's that are greater than 5. Connect it with the word or, and then we write our negative positive. So we take what's inside the absolute value, make it the opposite. So when I distribute my negative, subtract 3. Now here I have to divide by a negative again, so I get t is less than negative 2. So I need to graph those. So all the t's that are 5 or bigger. So let's just put 0. This is the number 5. So I want all the t's that are bigger than 5. And I do not want to include 5 because there's no equal to. The next inequality says all the t's that are less than -2. I don't want -2, but anything that's less than that. And this is an OR graph. So OR means either or. I don't need where they overlap. I just want to put them all together. So what numbers did I shade in? My final answer, all the x's that are less than -2, or all the x's that are greater than 5. Our last example for today, let's go ahead and notice that the absolute value symbol is not by itself, right? There's a -7 and there's a ×2. So we need to undo those before we can do anything else. So our first step would be undoing the -7 with a +7. So 2 times the absolute value of d plus 1 is greater than or equal to 6. And as I mentioned before, I don't want the absolute value to be multiplied by 2. So to undo multiply, we would divide by 2. And now we get the absolute value of d plus 1 is greater than or equal to 3. So now the absolute value is all by itself. And I can compare the inequality symbol and see that the inequality symbol is opening up towards that distance. So again, the absolute value symbol means distance. And if it's opening towards that, that means it's the biggest. So it's more than something. In this case, it's more or equal to 3. But whenever we see something with a more, right, from our investigation, more means or. If I want more distance, I have to go away from something. So I know that this is going to be an or compound inequality. So once we have our absolute value by itself, again, we write our positive, and our negative, and we simply separate them with the word or. So our positive, we keep the inside of the absolute value, and then we keep the symbol and the number, so we'll just subtract that right away. So all the d's that are greater than or equal to 2. Let's go do those right away on our number line. So all the d's that are greater than or equal to 2, so we can put 0 on our number line, and we do want to include 2 because of the equal to, and the numbers that are bigger than 2 are this way. Now for our negative-positive version, we take the inside of the absolute value, put it in parentheses so we can take the opposite of everything, and then we keep the symbol and the number. So we'll distribute our negative, we'll add 1 to both sides. Now here I have to divide by a -1, so of course we know to flip the inequality symbol. And I'm just rewriting my word or so I can see that these are connected by the word or. So we need to go graph that inequality, all the d's that are less than -4. So here's -4. We do want to include -4 because of the equal to, so less than or equal to -4. So this number is -4, and all these numbers are less than. So if it's an or, we're not looking for the overlap. We're just saying what numbers did we shade in, one or the other. So if your x was less than -4, you would work, or, sorry, less than or equal to -4, or your x's could be greater than or equal to 2. So that's our summary of how we solve, or that's how we solve absolute value inequalities. So hopefully you can go practice and do your homework now.